Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be measuring the favorability of a reaction using electrochemical potentials. So potentials is a way of monitoring the voltage or the amount of energy that passes in between our two cells, or our anode, where our oxidation is producing electrons, and our cathode, where our electrode is consuming electrons. And so we're going to go ahead and try to figure out exactly how much energy this reaction has by measuring the voltage of the system. So for some context, if you ever see something that reads, this is a 1-volt circuit, this means that each of the electrons traveling through that electrical circuit carries 1.6 times 10 to the negative 19 joules. And so if it has 10 volts, that means it will carry 1.6 times 10 to the negative 18 joules. And so by using these ideas, we can convert from voltage to the energy possessed by every individual electron, which gives us a lot of idea of how favorable a reaction may be under any given circumstance. However, it does feel like this is a little bit low of an energy. However, remember, we're dealing with individual electrons and not moles of electrons. And it turns out we've got a lot of electrons moving at any given time. And you can look at the rate at which these electrons are going from one side of the reaction to the other by measuring the current of the system. So if you've ever heard the phrase amps, that is a measure of current, which is just simply the rate at which electrons move through the system. So if I have a current of 1 amp, it means I've got about 6 times 10 to the negative 18th electrons being transferred from cathode to anode every second. Or if you're just looking at a wall socket, if I hook anything up into there, that would be the number of electrons that are being transferred to you. So this is a good context for what we're looking at when we're looking at electricity. Voltage measures the amount of energy an electron has. Amp shows how many electrons are coming through at any given time. And using this, we can look at the favorability of chemical reactions. First thing to make note of is the Sine Convention. So unlike when we were looking at free energies, a favorable reaction has a positive voltage, meaning that those electrons are carrying excess energy. So unlike what we've seen before, what we find is that in electrochemical systems, reactions tend to go from low, unstable reactants towards high potential, very stable products, because high potential means that they've got a lot of energy, they've got very low energy, and those electrons can give off all that excess energy as they travel from one side to the other. However, part of the problem with trying to look at these electrochemical cells and just measuring the potential is I don't know which of my two half reactions is more important. Is it that forming copper solid is really favorable, or is it that forming oxidizing zinc to form zinc 2+ is really favorable? In order to try and evaluate this, we need to try and break our potentials, just like our reactions, up into half reactions. And so one of the ways we can do this is taking our cell energy and saying, well, the energy for the total reaction is going to be the same as the energy to reduce my for my reduction half reaction, plus the energy of my oxidation half reaction. So if we look at zinc, it turns out that this is our oxidation reaction, and it turns out this is a fairly big number, meaning that this is fairly favorable. Those electrons that we're producing, very high energy, looking good. However, if we look at copper, this has a reduction potential of 0.34, meaning that this is also very favorable. Electrons really want to jump on copper ions to make that solid. Again, both of these are very favorable reactions, so if you add them together, it is a very favorable reaction. But again, zinc is a little bit better of a reducing agent than copper is an oxidizing one. But what we end up having is, by looking at our potentials, we can see that all three of these reactions are very favorable as written. Larger the number, more favorable. However, one of the things I want you to make note of is all three of these potentials has a 0 as a superscript. This 0 is called a not. And this not superscript indicates that all of our concentrations, just like for Gibbs, are under standard state. So when we saw not for Gibbs or entropy or enthalpy, that meant standard state. And it's the same definition we had before. 1 molar for aqueous species, 1 bar for gases. And again, the electrons won't really count towards either. So again, make note, we change the concentration, these potentials may end up changing, and we'll bring that up later. So one of the unfortunate bits is previously we said, okay, we can just add the reduction action and the oxidation reaction. We have a problem in that sometimes I might want that oxidation reaction and sometimes I want the reduction reaction. And do I really want to report both values? So as a result, it's convention that if you go ahead and look up all these values, they're always going to be presented as reduction reactions. So that works just fine for a copper reaction. So if you go ahead and look up the copper 2 plus copper potential, it will refer to this reduction reaction. However, if you try and look up zinc, it will actually refer to the reverse reduction reaction. And you can transform in between an oxidation reaction and a reduction reaction simply by switching the directions of the reactions, and that corresponds by switching the sign of the potential, which makes sense because if oxidation is very favorable, it means that reduction is very unfavorable. And that's exactly what we see with the signs. However, if I'm going to end up reporting all my values as reductions, I can't simply get my cell reaction by adding these two reduction potentials together because, well, that just doesn't work. So one of the ways you can do it is try and turn all your reduction reactions into oxidation reactions and add those together. But the much more common method is to essentially say, I am going to take my cathode, so my normal reduction reaction, take that potential, and I'm going to subtract out the reduction potential of my anode, which is the same thing as flipping the reaction. So taking the negative and adding them together. So it turns out we can find our E cell by doing our cathode, that 0.34 for copper, minus the anode, which is minus that negative 0.763 for zinc. And we'll find out that is indeed still that very same favorable potential we had. So again, what we're really seeing here is reduction reactions will have a very high favorable potential, but a favorable oxidation reaction will have a very low reduction potential, really helping drive the system forward. However, one of the problems is if I'm going to go ahead and try and determine this potential, it can be a little bit difficult because this would be the energy of the reaction. But what we haven't specified is where those electrons are coming from. I can't just go measure the reduction of zinc and get a potential because electrons have to come from somewhere. They don't spring out of the earth. So we need a standard source of electrons to count as the zero potential. So this is called a standard reference cell. So whenever you look up a potential, make sure to always see what their reference cell is. There are about 3 or 4 very common ones, but we're only going to deal with the most common system, which is called the standard hydrogen electrode, also known as SHE. So one of the big things is that this reaction assumes that all of our electrons come from the oxidation of hydrogen gas. So H2 goes to free protons. And again, standard state, so that means 1 bar H2, 1 molar protons. So this is designated as having an oxidation potential of 0 volts. You may note that I put a negative here, and it's a common trick to illustrate that what we're often going to have this potential reported as is as a reduction potential, which is -0, which is 0. So this is our standard reduction potential, or of 0 volts. So any other potential I measure is usually reported under this standard hydrogen electrode, meaning that at some point, somebody probably hooked a given reaction up against the standard hydrogen electrode. In this case, if I want to know the potential for zinc, I'm going to have to hook up a cell where I am oxidizing zinc versus a standard hydrogen electrode where I'm feeding in hydrogen, producing protons. And again, note I'm reporting both of the reactions as reduction reactions here. And so I can get the potential for this cell by taking my cathode, in this case, the zinc reaction, minus the standard hydrogen electrode potential. And if I measure this potential at negative 0.763, well, I know that the standard hydrogen electrode is 0 volts. So ta-da, that means that my E cell equals the potential of the zinc, and this is how you can directly measure the voltage. So if you set up one of these standard reference cells where you compare whatever the species of interest is against the standard hydrogen electrode, the potential of the cell is the potential of the reduction reaction occurring at the cathode. However, one of the things that is worth noting is we do have a negative potential here for zinc. So really what we do perform when we measure the system is saying that this reaction doesn't want to occur. Zinc really doesn't want to become reduced. It'll want to go the reverse direction, become oxidized. Now, one of the problems that we have is I can't exactly set up a standard hydrogen electrode. It involves a lot of flammable gas and some pretty acidic conditions because I've got 1 molar protons and I don't like working at a pH of 0. So one of the common things you can do is set up a different sort of electrochemical cell where you set up the reaction of interest against an electrode of known potential. So let's say I know the potential of my zinc electrode reaction. It has a reduction potential of negative 0.763. Now what I can do is by measuring the reduction of silver against this zinc reaction, I can determine the reduction potential for silver, knowing that the whole cell potential is about 1.5 volts. So I can do this by first splitting out that zinc reaction and then finding my silver reduction reaction. So I don't know this potential, but I know the potential of my cell should be the reduction potential of my reduction reaction, cathode, minus the reduction potential of my anode, in this case, zinc. So doing this, I can rearrange to solve for the potential of silver, and it'll be my cell reaction plus my zinc reaction. In this case, about 0.8 volts. And there you go. That is the reduction potential of silver. However, most of the time, we're just going to go ahead and look in your book and find a big table of standard reduction potentials. It has a lot of very common relevant species, and we have the reduction reactions listed here on the left, and some example electrochemical cells, as well as, most importantly, the involved reduction potentials. And one of the things that's worth noting is if I'm trying to figure out which reactions or which chemical cells are going to be most favorable reduction reactions are going to be the ones with high potentials. So for example, fluorine gas, ozone, hydrogen peroxide, all of these are readily reduced into their corresponding species. However, if I've got a very low potential, so something here like lithium ions don't want to become reduced. Instead, they're going to want to do the reverse reactions. So whenever I have a reaction down here, so anything really below the standard hydrogen electrode, these are species that are very readily oxidized. And so what you'll note here is we have a lot of our metals, and one of the reasons they undergo oxidation so readily is they very easily lose electrons to usually somebody who wants those electrons a lot more. So hopefully this gives you a reference for when we're talking about favorability of electrochemical or redox reactions, how we can figure out who is more or less favorable. However, we're going to go next time spend a little bit of time of linking this idea up to our much more familiar Gibbs free energies. Until then, take care.